So welcome. So let me get my pen going down here. And ink cold, and we'll have red for today, I think. And so today we're going to do the second part of heat and thermodynamics. And whereas before we're looking at things like conduction, convection, and radiation, with a fair bit on radiation, now we're going to look at the thermodynamic laws. And we've mentioned one already, I think, which is the zeroth law, but in case we haven't, let's review it. You see this written in complicated ways and simplest ways, but the simplest way I can express it is if two objects are in thermal equilibrium, when heat does not flow from one to the other, two objects are in thermal equilibrium when heat does not flow from one to the other, despite the fact that they are in thermal contact. So a couple of new phrases there. Thermal equilibrium means that basically they have the same temperature. Thermal contact means that heat can flow from one to the other. So if I am in contact with a desk and heat does not flow between me and the desk, we are in thermal equilibrium. And this will occur when we have the same temperature. That's what basically this is saying. If two objects are in thermal equilibrium, they have the same temperature. You see it sometimes in physics textbooks written in a very convoluted way about object A and object B and object A and object C, and then it basically says if I'm the same temperature as the wall and the wall is the same temperature as the floor, then I'm the same temperature as the floor, which is it seems a bit obvious. And it's kind of weird that you have the zeroth law. You don't normally name things the zeroth anything. And so what happened with this, I'm pretty certain what happened is that they named the first law of thermodynamics, they named the second law of thermodynamics, and people were still getting stuff wrong. And they realized, we got to go back and clear up something that's more fundamental. So rather than calling it the third law of thermodynamics, they called it the zeroth law of thermodynamics. That's just, I guess, a historical issue. So what we say is if A is in thermal equilibrium with B, and B is in thermal equilibrium with C, then A is in thermal equilibrium with C. And the analogy I like to use is if A is as rich as B and B is as rich as C, then A is as rich as C. And that seems very, very obvious. The link that's not there, I think where people get confused, is that there's a link between internal energy that's the thermal energy that's inside an object, and temperature. They're not the same, but if I increase my internal energy, my temperature must increase, and if I decrease my internal temperature, my temperature must decrease. And then the other thing is that people, I think, sometimes think that objects compare themselves based on the amount of internal energy when they don't. They compare themselves atom for atom. And all the atoms know about is their temperature. If I'm part of an iceberg, I don't know how big the iceberg is, so I don't know how much internal energy is. I just know that I've got a certain energy, average energy per particle, which reflects my temperature. Cool. So it's a little bit of a convoluted picture. Then let's look at the first law of thermodynamics. And the first law of thermodynamics is again, we're dealing with internal energy, so we've got to be clear that internal energy is the total amount of energy inside our object based on its motion relative to itself. We can't put it in the back of a car and make it go faster and say it's got more internal energy. It's got more mechanical energy, but it's not got more internal energy. So there's a kind of subtle distinction there between the energy because the whole thing's moving and the energy because these atoms are moving. It's different. And also what's not necessarily clear is that there's two ways of changing the amount of energy inside an object. And one way is we can heat it up or cool it down using heat in or heat out. And the other way is we can do work on it or have it do work on us. So if you rub your hands together, you can feel heat being generated, and that's doing work, causing, converting work to heat. We can also get, and it's not so obvious with solids, but with gases, for example, they can expand. And if they expand, then they reduce their internal energy, and because they're doing work on the outside, and their temperature falls. And if you've ever taken one of those air horns or a fire extinguisher or something, anything that's got a propellant in it, and you just squish it, paint, if you do aerosol paint, and you just squish it for a long time, the can gets cold because the propellant that's inside is converting from liquid to vapor, and it's doing work. There's an expansion involved, and so you get a cooling effect. So we say the change in internal energy of a system, an object, is equal to the heat flow into or out of the system and the work done on or by the system. And so you can get these weird situations where I can have a beaker filled with a canister full of gas, and I can put a Bunsen burner on it, and I can have the temperature of the gas decreasing. And it just seems very counterintuitive. How can the temperature decrease when I have a Bunsen burner acting on the gas? And the answer is that, yeah, I put in 100 joules of heat, but I take out 200 joules by expanding the gas. So if I heat and expand, I'm doing two opposite things. Now, if we use a money analogy, I actually think this is a good analogy. If you said to me, oh, the most amazing thing happened. I put in $100 I went inside the bank and spoke to the teller, and I put in $100, and then later on, my bank account had less money in it. How can this be? Then the obvious answer is, yeah, and you also went to the ATM machine and you drew out $200. There's no magic here. You paid $100 into the worker, but you took $200 out of the machine. I know how you did this. It's not some magic or some crime. You just use the two ways in and out of your bank account. It's the same thing with the heat. Yeah, you used a Bunsen burner to put energy in, but you might have expanded it to take energy out. So, and it seems sometimes to me, when you read the textbook, that it's almost like they don't want to really emphasize that, so they can ask you a whole bunch of questions about it. Just think of the bank analogy. Mathematically, what would we say? And I got to tell you now, we are in a time of educational transition. It doesn't happen very often, but traditionally, the chemist said, my change in internal energy, sometimes called delta E, is equal to Q plus W. And the physicists would say my change in internal energy is equal to Q minus W. And you think, how can they disagree so much? And the answer is they had opposite definitions for the sign for work. So a chemist would look at things from the gas's point of view. And the chemist would say the expansion of a gas is taking energy out of the gas. So expansion is negative. A physicist looks at things from the engine's point of view, and this is often to do with heat engines. So from a physicist's point of view, the expansion was pushing on the environment, and so expansion is positive. So can you see we have the negative sign going into a positive thing, and here we have a positive thing going into a negative sign. So because they had opposite definitions, they had equations with opposite operators. on it. And as long as the chemist stayed doing chemistry and the physicist stayed doing physics, there was no great confusion. And then, I think about 4 years ago, the textbook that we use for general physics changed the sign convention and started doing it the chemistry way. And so not so much with you guys, but with my physics 1 people, my homework is done using one sign convention, and my notes now say the other sign convention. So I got to square that off. And this is what happens in education. The science is correct either way. It's just trying to make things so that there's consistency and there's agreement. And this is one of the few times, I think, when physics, at least in terms of these authors, has capitulated with chemistry. Usually there's no quarter given and no quarter taken. So we're going to do it this way, because I've left the notes like this, and later on I might change the notes for another semester, but basically I'll look and see what our book says, but basically this is the convention for us. So we can do an example of this, and we say, okay, 10 joules of work is done on a cylinder of gas by compression. So here's my internal energy, sometimes called thermal energy. That's the sum of all the particles' energies that make up my solid. And in this case, I have work been done, compression, so I have 10 joules of work. And 30 joules of heat is added by the application of a heater. So this is 30 joules of heat. And it's asking, so what's my change in my internal energy? So my delta U, which would equal, let's do it the physics way, Q minus W, delta U is equal to Q, which is 30, minus, now this is a compression, so that would be minus 10. Yep. So this would be 30 plus 10, which equals 40 joules. And that makes sense if you look at your diagram. With the way that I've done the diagrams, 10 joules is going in, 30 joules is going in, 40 joules must have gone in. Unfortunately, you're not given the diagram when you do the test, so you got to, the arrows kind of give it away, but the arrows won't be there on the test. So you've got to look and say, is it a compression or is it an expansion? If it's an expansion, it's a positive. If it's a compression, it's negative. And am I heating or am I cooling? Maybe I'd put an ice pack on there. If it's an ice pack, I'm cooling. If it's a Bunsen burner or the like, I'm heating. So they're not hard. Mathematically, they're trivial. It's just getting the sign convention right that's the issue. So this would be answer A. Cool. Okay. So we can kind of apply this to heat engines. Okay, so I've got something here. Okay, I'm a bit caught off guard here. So application of the first law on the fire extinguisher. So the total energy in an isolated system must be conserved. So in a fire extinguisher, expanding CO2 draws down the internal energy of the cylinder faster than the ambient temperature can heat up. As a result, the fire extinguisher gets colder. We're doing a lot of expansion, which is taking energy out of our system. And so the internal energy is decreasing, and that's decreasing the temperature, so it feels colder. Okay. So let's draw a little bit of a line around there. I want to talk about this next bit, which is heat engines. I think I've combined 2 pages here to save space, and I think I've done it too much. So heat engines. We can talk in terms of a steam engine. We don't see many of those around, but you might. There's a place down, is it by Sarasota, where you can ride a steam engine? I can't remember. There's the Florida Steam Locomotive Enthusiasts. They run a place, and you get on this train, you get pulled by a steam engine. Car engine is also an example of a heat engine and a gas turbine. Gas turbines are used in power stations, and basically you get gas coming in, it spins a wheel, which makes electricity. And these are ways of converting heat into work. It's the way it's done. And so for them to work, it's like we need a hot reservoir, and that's our fuel. Simplistically, that's so with a steam engine, the fuel is coal or wood, or these days natural gas. And in fact, if you go to Busch Gardens, they have a natural gas locomotive there in Busch Gardens. So that's the fuel, and that's used to make steam, which then is used to work the engine. So the steam carries the energy rather than creates the energy. Okay, so we have a hot reservoir. That would be our steam, or our heated, or our air fuel mixture in a gasoline engine. And when we burn that, when we ignite that, when we use that, it's hot. And normally the energy would just go from the hot to the cold. If you took a gallon of gasoline in your backyard and set it on fire, you'd warm up the environment. It wouldn't do you any good, wouldn't do the environment any good, but it would go to the environment, because the gasoline flame would be hot and the air would be cool. Then along came people like Stephenson and Watt, and using steam. What the story is that Stephenson was making a cup of tea, which British people do a lot. He was boiling the kettle, and on some kettles what they have is they have a little whistle or a flapper, and what happens is as the steam comes out, this thing flaps backwards and forwards and tells you, I'm boiling, you know, tap, 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 I'm boiling, or whistle, 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 I'm boiling. And story has it that he saw the flapper going flap, 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 and said, whoa, that steam's doing work. If I could connect a machine to that flapper, in principle, I could do pushing and pulling and all that. So he messed with it and messed with it and messed with it and came up with a very crude steam engine. Not very efficient, but it caused motion. Not a locomotive. Just a standing steam engine, just something that turned a wheel, which pushed a rod, which could be used for anything you want to push a rod with. Now, I'm sure they didn't know, but what was going was they were taking energy from the hot reservoir, in this case steam, and on its way to the cold reservoir, they got it to do some useful work. Now, the ironic thing is that the engine doesn't care about useful. It doesn't know the term useful. It just knows I became mechanical for a while. And mechanical systems all have some degree of friction. And friction turns mechanical energy back into heat. So it actually ends up all going here again. There's no way around it. It all ends up at the cold reservoir. But with a steam engine or with an internal combustion engine, it also, for a while at least, does some work that you consider useful. And this was the most amazing breakthrough in terms of society. For the first time, you could get rid of beasts of burden or people, and you could use a mechanical machine, basically, an engine. And it turned out that some places like Britain were lucky in that they had a lot of coal, and France not so much, and Spain none. And so the world got divided into the haves and have-nots. And if you had a lot of coal, then you had a lot of free energy. Your machines worked. Now, as a individuals, you had to buy the coal to run your steam engine, but you were buying the coal from somebody in your community, and so they got rich and they'd spend money, and you know, it all goes around. Whereas if you're in a place like Spain, you might not invest in these engines because the fuel was too expensive. And it's been that way kind of ever since, really. I mean, Britain had its fortune when coal was king, and then when oil became king. Britain actually found oil in the North Sea along with other European countries, but for a while there was a real bit of a problem because we had coal but we really wanted oil. And then we had a little blip when we had a lot of oil, but that's now gone. And so now we don't have really any coal, and we don't have really any oil to speak of. And so now we're transitioning in Britain, transitioning into a society that is not blessed with much fossil fuels. And so we're going to find out what it's like for the rest of the world. And America, which came to the Industrial Revolution later, had coal, but also when oil was like really valuable, had the oil. And to some extent it drove the oil economy. The interesting thing is all these fossil fuel reserves are becoming more and more problematic. Not only because of the environmental issues, but just because a lot of it's been used up. And when things get used up, they get scarcer and scarcer, and that means more and more expensive. And so now we're at a stage where, according to recent news reports, renewable energy in many places is now more economical than fossil fuels. So that means that for many countries, the cheapest way for them to go is to use solar or wind, etc. And the wind goes everywhere, and the sun shines everywhere. Even in Britain, the sun shines. So it's actually going to be, I think it's going to be fascinating over the next 50 years, you know, your generation's time, because countries that have been starved of resources, once the renewable, what we call renewable energy, once the renewable energy markets become well established, you know, you could be in a relatively fossil fuel, you can be in a fossil fuel neglected part of the world and have as much energy. It's a democratization of energy. It comes down to how much energy per square meter do you have. You know, and a lot of countries that don't have any oil have a lot of energy per square meter when they look at renewables.
Do you think like gas stations will, I mean like the oil providers are gonna like innovate, but do you think they're gonna stay with the oil?
So I don't know. My neighbour works for TECO and has a lot to do with renewable energy initiatives, and he's very keen. I mean, TECO put a whole bunch of solar panels in at the airport. I think the tendency is to stay with the technology you know. But I think that's dangerous for those companies. I think that they are energy companies, and solar energy is every bit as legitimate an energy as coal is. The issue comes that wind and solar don't lend themselves to the centralized power station model. They're much more like the European, not the English model, but the European model of having decentralized small power plants. So Europe's jumping on this. Europe is really, I mean, there are parts of Northern Europe, Denmark, for example, Germany, Scandinavia, where they are running energy systems, power plants at 90% efficiency, whereas for us a power plant is 30 to 35, maybe 40% efficient. And nuclear is less efficient than fossil fuel because of the safety issues of it. So it's going to be fascinating. My neighbor put solar panels on his roof. He got subsidies from TICO, and he got subsidies from the government, and it was not that expensive for him. He had to compete. He was lucky. It was a lottery. Well, not a lottery, but he had to be able to type his credentials in first to get one of these 80 slots to get it. That's not available to everybody, you know. It is, but you have to be one of the 80, you know. He's now not off the grid, but he generates more energy than his house uses. So TICO, he provides energy to TICO. You know, it's great. You can argue about, well, at night he's getting energy from the grid and during the day he's putting energy into the grid. But yeah, so it's a storage issue. It's just a storage issue. He says in 10 to 20 years we'll all be driving electric cars. He's convinced of that. I have another friend who's driving an electric car. He got a used Tesla. It was a 1-year-old Tesla. And he said it's not just the energy efficiency, it's the fact that when he's on I-4 and the traffic's backed up, he basically flicks a switch and his car just keeps pace with the car in front. So when it's this touch and go traffic which is driving the rest of us crazy, he's just like sat there doing work, reading, and it's just his car's just edging forward. He says that this car, he can click on his door thing and the car can come and get him from the parking lot. And he says he believes that's the thing that's going to really make these things take off. It's the convenience. He says he went to Atlanta, and he said that he was going to take his electric car to Atlanta because there's charging stations, these rapid charging stations all the way. So the infrastructure is going to be there. I think. So to my mind, I think there's going to be a change. I think that at some point we're going to turn around and say, I think the key is, I think as this market grows, the jobs are going to be in renewable. And I think at some point states are going to turn around and say, we're pushing this, and it will flip. My wife will buy solar panels when Home Depot or Lowe's sell and install them. When she can go to, like she can for a kitchen cabinets, we went to Lowe's. She says, when I could go to Lowe's and get solar panels, I'll buy it. While ever it is, you know, Florida solar that you've never heard of before, she goes, I'm not going near it because I have no idea if that company is going to be there in 10 years. But I know Lowe's is going to be there in 10 years. And when something like that happens, I think it'll start flipping. So exciting times. Hope I'm around to see it. It's going to be interesting. There's a little sum we need to do here, which is how much energy comes from the hot reservoir. And that's used to put energy into work, and it's also used to put energy into the cold reservoir. So we can say mathematically the workout W is equal to the heat from the hot minus the heat going to the cold. So I like the diagram, but the equation works just as well, you know. So heat engines, and that's what I just told you about. The total energy of an isolated system must be conserved. In a heat engine, heat is converted into useful work. So we're taking the heat and we're putting it into the internal energy of the substance, and then it's expanding and pushing against pistons, and we're getting the work out of it. I'd really like us to know, I don't care so much about steam engines. I did steam engines when I was at school, but that's because we had steam engines all over the place when I was at school, and not cars. We didn't have a car in our family until I was 22. We use trains all the time. Not so much steam engines towards the end. But we all have cars now. So let's look at this. This is the internal combustion engine. It revolutionized transportation, and we need to know about it. Four-stroke engine, because there are 4 strokes of the piston. The piston goes down, the piston goes up, the piston goes down, the piston goes up. And then it repeats. So 4 strokes. First stroke is so-called intake stroke, and that's where you draw the air and the fuel mixture into the piston. So the piston is falling down, drawn down, I should say. This intake valve is open. The reason why I'm drawing the valves like this is because this is the way they tend to be designed. They're not a top open valve. They go inside the chamber. And as this piston falls down, we create a vacuum, we draw air in. In an old-fashioned engine, these days like a lawnmower engine, if you have a 4-stroke lawnmower engine, you'll get the fuel mixed in with the air using a carburetor. But these days on a car engine, it's probably fuel injected. So they'll have a little nozzle and it will squirt just this little bead of fuel in at the right time, and it will do it very nicely. Either way, you draw in a fuel-air mixture. When you get to the bottom, as far as the piston can go, then the wheel spins and you start going up again. So we're in this next stroke. You close off your intake valve, so you trap this fuel-air mixture and you compress it. Because if you've ever, please do not do this, but if you've ever taken a firework and taken all the gunpowder out and lit it, it's not very exciting. It doesn't go bang. But if you leave it in the cardboard tube and light it, it explodes. And that's because that bang is letting the energy build up all at once and then having it burst out at once. So we hear all the energy at once. It's the same thing with this. If we were to ignite the gasoline when the gasoline was not very... if we were to ignite the fuel-air mixture when the fuel-air mixture had a big volume, we wouldn't get much. In fact, it would push it in the wrong direction. But by squishing it up and then lighting it, we get this nice big downwards force. So we have the compression stroke. We're compressing the gas. Both valves are closed. Piston is on its way upwards. Then, with both valves closed, we light the gas. So we have a little electronic spark typically. In a diesel engine, this happens spontaneously because of the compression ratio. But in a gasoline engine, we have a little spark which ignites the gas. It heats up the fuel very quickly. The gas expands, and so we push the piston down. When we get to the bottom of our journey, again, the piston starts moving back upwards. So we open up the exhaust valve and we let this burnt gasoline and air mixture out. So down, up, down, up. It turns out there's only one of those 4 strokes where we get energy out of the gasoline, and that's in the exhaust. Ironically, in the other 3 strokes, we're using the mechanical energy of the car to make the engine work. We have a flywheel in the car which actually helps this thing run smoothly. So, and the other thing I have to say is that when we exhaust our gases, they still contain fuel. The fuel is not completely burned. And the reason for that is that to completely burn the fuel, we'd need to allow the piston to expand and expand and expand and expand and expand. And it would slow down as it's expanding. And so we would lose power. We would get more efficiency, but we'd lose power. And there tends to be a bit of a fight between efficiency and power. I'd like you to be able to name these in order. I'd like you to know what the exhaust valve is doing and the piston are doing in each case. So I'd like you to know when both valves are closed and the piston is on the way up, you're in the compression stroke. I'd like you to know that the spark plug spark starts off the power stroke. So that's what I want you to know from that. Online, I think I have some videos showing the inside of this engine running. And if we're not, I'll show you it before we finish class today. Let me put my glasses on so I can see. Yeah, go. So, what is the name for the stroke in which the inlet valve is closed and the exhaust valve is open? Well, I'm sorry, but that's not enough information. Because no, actually, no, that's fine. Yes, it's fine. It's there's only, because the exhaust valve is open, there's only one stroke where that can happen, and this would be the exhaust stroke. So let me just talk our way through this. For the intake stroke, the intake valve is open, and the piston is moving down. For the compression stroke, both valves are closed and the piston is moving up. For the power stroke, both valves are closed and the piston is moving down. And for the exhaust stroke, the exhaust valve is open and the piston is moving up. So there's never an alternative where the exhaust valve is open and the piston is moving down. I'd like you, from the hints of this valve is open or this valve is closed, this piston is moving that way, to know what stroke it is. So for instance, on the power stroke, both valves are closed, but the piston is moving down. Okay. That kind of thing. Now, the other thing I could ask you about is the efficiency. And the efficiency is what you get out, and you get work out, over what you put in, and you put the Q hot in. So that's another thing. It comes later in the homework, but efficiency. We've done efficiency before, I think, mechanics. And we defined it, and so I tended not to define it straight away here, because we kind of know it, but we need reminding of it. Okay, sufficiency. Now, that's amazing, but there was a second wave of amazing, and that was when people started looking here and saying, wouldn't it be great if we could reverse this? So rather than using heat to do work, maybe we could do work to create, rather than we could do work and push heat around, not create heat, but push heat around. Well, I can do work but that's not what they mean. They mean doing work and getting the energy to flow from the cold reservoir to the hot. That makes no sense from a spontaneous point of view, because the cold reservoir has a lower temperature than the hot reservoir does. So that's a bit weird. But they found they could do it with things like the refrigerator. So what they found, let me explain this. Do you remember we did the graph of temperature versus heat, and we had this graph here where this was solid and this was liquid and this was vapor, yeah? And what I said was these are not as wide as they should be. Well, what somebody realized was, if I can vaporize a liquid mechanically, it will draw in a lot of heat, because it's like the mechanical method of causing the vaporization still requires that the liquid get the vapor, produce a vapor, which is thermodynamic. So I can grab a whole bunch of heat by causing something to vaporize. And then I can get all that heat back when I cause the thing to liquefy. The difference is I don't have to do them in the same place. So the cold reservoir link and the hot reservoir link need not be in the same place. And so we started getting to the situation where I could take Freon, for example, and I could pump on Freon, which would cause it to vaporize, which would chill that environment. And then I could take that vaporized Freon into my backyard and compress it and cause it to liquefy, which would heat up that environment. And it didn't matter within reason how hot the backyard was. I could still dump thermal energy there by mechanically causing condensation. And within reason, it didn't matter how cold the room was. I could still cause cooling by vaporizing inside the room. And I can keep track of it using this diagram. So rather than work going out, I can put work in, and I can cause the grabbing of heat from a cold reservoir and the dumping of heat in the hot reservoir. And it's completely counterintuitive, but that's the way your refrigerator and your AC system works. That's the way it works. Now, we don't use Freon anymore because it was, unfortunately, and this is one of those times when I've got a lot of sympathy for industry. They picked Freon because it seemed like it was completely inert. They did not want something which would rust the piping. They did not want something, all that kind of stuff. They were very careful. It wasn't poisonous. You couldn't breathe it instead of air, but you know, if you got a whiff of it, it wouldn't kill you. All that. It was no more dangerous than an awful lot of other industrial things. So it was like seemed pretty safe. And unfortunately, when you put it into the upper atmosphere, it breaks up the ozone molecules into oxygen. And unfortunately, the ozone is what keeps out the ultraviolet to a great extent. And so, unfortunately, we ended up punching a hole in our ozone hole, which led to an awful lot more, destruction of things like plankton in the southern seas, and also skin cancers in Australia. Australians, very outdoors country, took sunshield really seriously, whereas in the States, many people don't even worry with sunscreen. If you're around Australians, they take it very seriously because they were very concerned for skin cancers. I'm going to just pause. So they tried very hard to not cause damage with Freon, and unfortunately, because of the ozone hole, it did. And the really good story is that and America did this. America unilaterally banned Freon. They didn't wait. They didn't say, well, we can't sell our refrigerators, in Canada anymore. They just said, we're banning it. You can do what you like, but we're banning it. And then other countries, because nobody wants to be the one who loses out, other countries said, well, if you ban it, we'll ban it. So other countries join in, and very quickly the developed world just banned Freon. And there were people who kept some and would use it, but by and large people stopped. They stopped manufacturing it, they stopped using it, they stopped supplying new refrigerators with it. They used alternative chemicals which were less problematic, and the ozone hole started recovering. And pretty much within a reasonable time, if it's not gone now, it will be gone relatively soon. That's a really wonderful success story about one big country taking unilateral action and setting the tone that the rest of the world will follow. And, on a personal basis, I think it's one of the sad things is, somebody's got to take the lead on things like carbon dioxide, and we're not, for various reasons we're not. All right, so we have refrigerators, and whatever liquid they use, they don't have to use Freon, but whatever liquid they use, they look like this. They consist of a tube, basically, incredibly simple. I've got to find my pen. They consist of a tube, and the tube is divided into two bits, so they have a little constriction there. It's just a narrowing of the tube at some point to make it into two parts. And they have a pump, and the pump draws on one side, which is the low pressure side, and that mechanical reduction in pressure causes vaporization. And on the high pressure side, that increase in pressure causes liquefaction. Now, the mechanical creation of the vaporization still requires that thermodynamically heat is taken from the environment. And the condensation requires that heat is dumped into the environment. So we're mechanically causing a thermodynamic change. And so all you do is you put the vaporization where you want cooling, you put the condensation where you want heating, and you're happy. You got the system. So we say a heat pump can cool a house if the direction of the pump causes vaporization within the house. Energy is dumped outside the house, no matter what the temperature is there. If it's the same temperature as the sun, everything melts. So, within reason. I'm not saying that under all circumstances. I'm saying within reason. While the system is functioning, it'll work. A heat pump can heat the house if the direction of the pump causes condensation within it. Energy is taken from the outside of the house, no matter what the temperature is. So, in principle, you could flick the switch and change the direction of the pump on your AC system and have it as a heating system. Frankly, my AC system has a little gas furnace underneath. And I suspect most AC systems have a gas furnace underneath because it's just quicker. But in principle, you can just flick the switch and reverse the pump. A heat pump is set to heat the house in winter. Where is the vapor condensed? Well, wherever you have condensation, you have heating. So if I want heating, heat inside, then condense inside. So in this case, if I want heat the house in winter, I want condensation in the house. If I wanted it to cool in the house, I would have vaporization in the house. Cool? Almost there. This is basically just saying heat can flow spontaneously only from a hot source to a cold sink. Well, when we use a heat pump, it's not spontaneous. We're really messing with it. No heat engine can be constructed in which heat from the hot source is converted entirely into work. Some heat has to be discharged to the sink at lower temperature. We can't have a 100% efficient heat engine. You can't have all the energy goes into the machine and none of it goes directly. Because the way that works is you're only going to get this thing to work if there's a temperature difference. And as soon as there's a temperature difference, you're getting some of it going, just straight into the cold sink. But if an efficient engine, you'll get most of it going through the engine and not much of it going directly up the exhaust pipe. And if it's a poor engine, a lot of it goes to the exhaust pipe and not much of it goes into the engine. So basically, I'm always going to have this. I can't have that be zero. So there we have it. And we can talk about efficiency. Efficiency, remember, is the work over the work out over energy in times 100%. Well, if we want to put it in terms of what we deal with, Q hot minus Q cold equals work over Q hot times 100. And I don't like this. It's just like this because it wants to look like that. And it's in the books like this, but I don't even remember this. I can divide Q hot by Q hot and get 1. And I can divide Q hot cold by Q hot and get Q hot, Q cold over hot. I can get this from there, so I don't even bother with that. I just bother with that. The theoretical limit is done with a thing called a Carnot engine. And this is as good as it gets. You can't make a Carnot. You can approach it, but you can't make it. And that has the limit where this is, depends on the ratio of the temperatures. And what you find with this is your efficiency gets better the smaller this fraction is. And this fraction is small when you have really hot fuel and a really cold sink. So the temperature in the environment affects your efficiency of your motor. I used to have a little Honda motorbike, little Honda 50, and I would notice on cold, rainy days it would run great, and on summer days it would not so work great. And so I took that as being part of this. But it turns out that I had a carburetor, and on cold days the carburetor would gather more fuel, and on hot days apparently didn't gather as much fuel. So that was also part of it, which is a mechanical thing that I didn't appreciate. What is the efficiency of a heat engine that takes in? So let's have a look. So this is a heat engine. So this is the hot, and this is the cold, and takes in 60 joules. And it does 12 joules of work. So what's efficiency? Well, efficiency equals what you get out, which is the work, over what you put in, which is Q hot. So the efficiency is equal to the work, which is 12 over what I put in, which is 60, which is 0.2, which is 20%. Equals 0.2. That as a percentage is 0.2 times that as 100, which equals 20%. So let me just, I can express efficiency as a fraction, that is between 0 and 1, or I can express it as a percentage between 0% and 100%. And the way I get is I take the fraction and multiply it by 100. I can be a little bit, I don't know what the word is for this. I can be a little bit, I can make it a bit more interesting. I don't have to give you just those two numbers. I could say that this is 48 here. I could give you the 60 and the 48, and then you'd work out the 12. Yeah? So I could do that as well. I could say this equals Q hot minus Q cold over Q hot. And then I know my Q hot, I know my Q cold, and I've not mentioned the 12, but you can do it that way. Power station, 30% efficient, 30 to 40. Automobile engine, about 30% efficient. Light bulb, well, light bulb it's not a heat engine, but light bulb would be, an old-fashioned light bulb would be about 2% efficient. Outrageous, yeah. They're banned in Europe for good reason. They are incredibly wasteful. I mean, you want the freedom to use something that's wasteful. Why on earth would you want the freedom to do that? You know? When you had the Easy Bake Oven, the Easy Bake Oven was what the light bulb should have been invented for. It wasn't, but I mean, it's 97% efficient at heating. It's only 5% efficient at lighting, so only about 3% efficient at lighting. Energy degradation. This is a philosophical bit. Basically, you can't have a heat engine without a hot bit, and you can't have a hot bit without having concentrated energy. So things like coal and natural gas and nuclear energy power are incredibly valuable because they are local concentrations of energy. Well, the sun is also a local concentration of energy. It happens to be somewhat distant. It sends its energies to us via light, but it's an energy source just like anything under the ground is. But we need these hot sources of energy. And when we've used up all of a fuel, there's still the same amount of energy in our system. It's just it's all at the same temperature, and therefore it's not useful to us anymore. So we talk about energy degradation. It's basically the hot bits get cool and the cool bit gets warm, and eventually we're all at the same temperature, and heat engines no longer work. It is better to have temperature difference between the source and the sink to be as big as possible to get biggest efficiency. This is why we notice small engines work better on cold, damp days. Yeah, well, it's also to do with a carburetor. As energy sources are dissipated, it is harder to get big temperature differences. The problem is not the amount of energy in the universe, it's that the energy is degrading. The energy available is degrading. If the energy is no longer in hot concentrations, it's no longer useful to us. 1,000 joules of thermal energy at 1,000 degrees C is the same as 1,000 joules of energy at 20 degrees C, but the 1,000 degrees C energy is much more useful. This energy resource has more available energy. This energy resource cannot be used to drive a heat engine, even though it contains 1,000 joules of energy is no longer available. This energy resource is degraded. And that's what's happening. Every time we burn something, we're degrading the energy. So I think this is something which is going to affect your generations more than mine. It's something that it's going to have to be addressed. And, I think I got to be just straight with you. I think it's part of my job. The physics for carbon dioxide in the atmosphere causing trapping infrared light is beyond reproach. That's physics. That's the way it works. The argument that the amount of carbon dioxide in the atmosphere being higher than it's been for a long, long time, that's, universally accepted among the climate scientists. I have met a climate scientist who does not think that what people do, it does not think that the approach for what people can do to try and avoid it, which is basically cut down on carbon dioxide production, is going to be effective at all. Basically says it doesn't matter what we do. Basically says this is one of nature's cycles kind of thing. But the vast majority of people look at the staggering increase in carbon dioxide in the atmosphere recently, last 100 years, and says it's the rate of change which is the real issue. And I was thinking about this the other night. I was reading this thing about, I saw this paper about the fall of Egypt, Greece, Rome, Egypt, the old Bronze Age societies around the Mediterranean. They've got different names, but basically Greece, Egypt, Cyprus, Syria, all those regions around there. And they were all very active. For like 500 years, they were like really doing well. Trading. These were a real hub of activity around the Mediterranean. And then within a very short time, they collapsed. And he was making the point that what happens is it's when you get like a perfect storm of drought leads to famine, leads to migration, leads to conflict, leads to trade routes being disrupted, leads to a fall off in your society. And when it's bad enough, it's not that we're all unemployed, but we know how to read. Within a couple of generations, we've forgotten how to read. Because there's absolutely, we're too busy scratching a living because society has come unhinged. And he makes the point that when you get massive changes very quickly, societies can become unhinged. And you know, it's kind of like, yeah, if the wheat belt moves into Canada, there's still a wheat belt. But if that happens in 10 years, the Canadians don't have the resources or the tradition or the population to take advantage of it. And the part of the American economy that's doing that is not Canadian. So we might end up with this ironic situation where, you know, people are trying to get out of the country as well as into the country, you know. And that's so people will move where they need to move. That's the world. If your family faces incredible hardship, you move. That's, in a way, what America's all about. And it's when motion has to come quickly. You know, in 20 years, you've got to move this population because otherwise they're going to starve. That's where you get big social problems. So the world will survive global warming. And yes, I did this thing the other day on television. Somebody was saying plants like carbon dioxide, and they do. We'll get huge trees. It's not that the world's going to stop, you know, being a green planet. It will be a green planet. But whether our societies, whether our social structures can withstand the rapid change, you know, because we have political boundaries, that becomes a real issue. It's not, as my friend once said to me, we're not saving the earth. The earth will do fine. We're saving people in the earth, you know, because we are more fragile than the planet is. So stuff like this becomes really important. Okay, sorry about that. I'll stop.